Hello and welcome to Vodcast 5.4. In this final Vodcast for Chapter 5, I will overview some additional evidence that supports the plate tectonics theory, and in doing so, we will also be studying Earth's history. Over the past 200 million years or so, our planet has undergone some significant transformation in terms of its land masses. In Image A, we see the supercontinent Pangaea, and this is what it would have looked like about 200 million years ago during the late Triassic period. If we shift our attention to Picture B, we start to see the breaking up of Pangaea. The first separation actually occurs between North America and Africa, and this is also when the formation of the Atlantic Ocean began. Let's now look at Image C. This would have been about 90 million years ago, and the next big split that we see was Africa from South America. One point I'd like to make about Image D is that you see India is isolated out in the middle of the Indian Ocean. Well, over time, India has ran into the Asian continent, and as India smashed into Eurasia, the Himalayan mountains were built. And then what's interesting about this picture is if we look at present-day Earth, it's really just a snapshot. And many millions of years from now, this map will have changed drastically, just as it has many, many times before. I'd like to overview the formation of the Hawaiian Islands. The Hawaiian Islands are being formed by a long-lived hotspot beneath the Pacific Ocean floor, and that hotspot actually originates below the Pacific lithospheric plate. The islands were formed by cylinders of upwelling hot rock, which we call mantle plumes, and although that mantle plume has kind of occurred in roughly the same position, over time the Pacific plate has moved, and as that plate's moved, that mantle plume has built a series of volcanic islands. If we start off by looking at the Big Island of Hawaii, we're actually looking at the youngest island in this chain. The Big Island is still volcanically active, and that's largely a consequence of the mantle plume. But as we work our way to the other islands, we notice that they're getting progressively older and older. We've talked significantly about erosion, and water is an extremely effective erosional agent. Well, over time, this hotspot will build up the islands, but the islands will be eroded away. As an example, if you take a look at the globe shown in this image, you see Detroit, not the city of Detroit, but rather what's left of a volcanic island that has been eroded away over a very long period of time. Detroit is now just a seamount, which is basically just like a little bump that's deep underwater in the Pacific Ocean. So what's really cool about this picture is the Hawaiian Islands as they exist today are beautiful and breathtaking, but they won't be there forever. Eventually they'll be eroded away, and it's very likely a new series of islands will pop up because of that hotspot in the Pacific Ocean. We're going to conclude this vodcast with two pieces of paleomagnetic evidence that I'd like you to know. I'm going to start off by defending my guy Wegener, because he didn't have access to the technology that could produce this kind of data when he proposed his continental drift theory. To summarize paleomagnetism as concisely as possible, certain minerals are magnetic, for instance magnetite, and when lavas that contain magnetite cool and crystallize, the magnetite minerals will align themselves with the North Pole, almost like little compass needles. And what's really interesting about that phenomenon is that if we study the alignment of those minerals over time, they will point us to where the North Pole was at that time. Over hundreds of millions of years, Earth's North Pole has wandered. In other words, it hasn't always been in the same location. And let's suppose you have two scientists studying the mineral alignment in ancient lava flows. One of those scientists is in North America, and the other scientist is in Eurasia. Take a look at the red path shown in Image A. Our scientists in North America would produce the red polar wandering track shown in this image. However, our scientists in Eurasia would produce the green polar wandering track shown in this image. The first thing you should notice is they have very similar shapes, so we do have consistency there. Our problem in this image is that our scientists wouldn't agree on the location of the North Pole at any given time except present day. In fact, there's about a 3,000 mile gap in between the locations of the North Poles based on their plots. Now, if you know anything about magnetism, it doesn't make sense at all to have two North Poles. That's simply not possible. But in Image A, we haven't accounted for the fact that the continents have moved over time. If we look at Image B and correct based on our knowledge of plate tectonics, we see that when you go back and form Pangaea and then work your way forward, we have very good overlap for polar wandering. So in summary, Image A shows the fixed continent model. If the continents never moved, data would indicate that we had two different polar wandering paths that are separated by a very large distance when studied from North America and Eurasia. Image B shows the plate tectonic model, and when we apply plate tectonics to the polar wandering data, we see a very good fit. The other piece of paleomagnetic evidence that I'd like to consider before concluding this podcast is seafloor spreading. On the last slide, I discussed polar wandering throughout time, but another thing that happens throughout time is the flipping of our magnetic north and south poles. In other words, the North Pole will become the South Pole will become the North Pole. As I've already described, certain magnetic minerals will align themselves with the North Pole, and they'll essentially point you in the direction of the North Pole. Well, scientists have extensively studied the seafloor, and I want you to take a look at this image on the right. In image A, we see what's called normal polarity. If you take a look at that divergent plate boundary and look at the white portion, those rocks look white because the alignment is with what we would consider today as our North Pole. And so long as the North Pole stays where it's at, the new oceanic crust being generated at that divergent plate boundary will continue to be the same color. But now if we take a look at image B, let's now suppose that the magnetic north and south poles have flipped, meaning what we would currently call the North Pole is now the South Pole, and what we would currently call the South Pole is now the North Pole. Well, now the new oceanic crust produced while this is the case will look red. So as long as we're dealing with reverse polarity, we'll see what's shown in this image as the red mineral alignment. And then in image C, let's suppose once again the North and South Pole flip-flop. So now the North Pole's back to where we would currently call the North Pole, and the South Pole's back to where we currently call the South Pole. The mineral alignment now will produce the white color that you see in this image. There are really two important science concepts on display here. The first is that we can now see concrete evidence that our magnetic north and south poles can flip throughout time. But the second piece of evidence, as it relates to plate tectonics, is that we have a historical record for the production of new oceanic crust, and that new oceanic crust is produced at a divergent plate boundary. A couple important things to note in this image is that the magnetic strips of rock will run parallel to the mid-ocean ridge, and the two possible configurations for those magnetized strips are normal polarity and reversed polarity. Okay, that concludes Vodcast 5.4, and this was the final Vodcast for Chapter 5. Chapter 6 builds on the knowledge and concepts contained in Chapter 5, and in Chapter 6 we'll study earthquakes and mountain building.